Key to Tomorrow, produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, the power station and the public. Your host, Dr. Warren F. Witzig, Manager of Reactor Physics, Bettis Atomic Power Division.
Welcome to another discussion on nuclear energy, Key to Tomorrow. In this discussion, we're going to talk about the power station and the public. And as an example of one of these, we're going to deal primarily with a pressurized water reactor. You'll recall from some of our past talks that in order to obtain the useful energy in nuclear energy, we must assemble fissionable material in a reactor and then obtain the heat from this reactor, transform it into electrical energy. Let us take a look at the pressurized water reactor cycle to see how this is done and to see some of the major components that are used in the system. There are really two systems involved, a high-pressure system and a low-pressure system. The high-pressure system must be assembled with great care. There must be no leakage of any of the radioactive material which may be in this system. The reactor core is housed in a reactor vessel. Water flows through it over to a steam generator, where the heat from the primary system is transferred to the secondary system. The water in the primary system continues on through a specially sealed, you might say hermetically sealed, pump, and then back to the reactor. The heat that flows through the steam generator into the secondary system boils water in this lower pressure system. The steam goes through the turbine and around in this cycle back to the steam generator. The energy from the turbine is used in an electrical generator to produce electricity that is very common to all of us. We're going to visit the office of a man that has played a very large role in the development of the pressurized water reactor for both naval and public utility application. We're going to the office of Mr. John Simpson, the Vice President and General Manager of the Bettis Atomic Power Division of Westinghouse. Let's go into Mr. Simpson's office. Hello, Mr. Simpson.
How do you do?
Mr. Simpson, we're ready to learn more about the nuclear power station. We wondered if we could start out by asking how the AEC brought about this development of the nuclear plant.
Well, Dr. Witzig, back in 1953, the Atomic Energy Commission had done a lot of development work in their various laboratories. They felt that the time had come when a full-scale commercial atomic power station should be built so that we could learn by actually designing and constructing a plant what the problems were so that better plants could be built in the future. At that time, the only type on which the technology was sufficiently advanced so that a plant could be built with a reasonable chance of success on a reasonable time schedule was the pressurized water reactor type, and that is the type used at Shippingport.
Could you tell us why the Shippingport site on the Ohio River was chosen rather than, for example, some remote reactor test site?
Well, it was felt that this type of reactor was sufficiently safe if correctly designed that it could be located in a densely populated area. And one of the major objectives, of course, was to learn how the plant operated as an integral part of an electric utility system, to let the electric utility people do the maintenance and do the operating so that the problems that would be encountered could be determined and ways found to improve the situation. The Commission looked around and asked for proposals from a number of utility companies throughout the country, and they chose the one submitted by the Duquesne Light Company as the best one, and so the plant was located here in Pittsburgh at Shippingport.
What then would you say is the main objective of the planning that has gone into this pressurized water reactor?
Well, the Shippingport atomic plant was not intended to produce economically competitive power. It was intended to produce knowledge, to enable us to learn how to build atomic plants, what the problems were, to get the developments done that would enable future plants to be competitive.
How does the electric utility actually use the nuclear plant compared to the coal-burning plant?
Well, of course, one of the things that we do is we use the plant as a part of a test program to get information on its operation for the plant operating people, for the physicists, for the metallurgists. And the utility company uses it in general to supply their peak load. That is, when their system is at a top load, they use this plant because, of course, this plant is still not competitive economically with the energy produced by coal plants. They do use it when one of their other plants is shut down for maintenance or repairs to supply the load for their system, or they use it to help them supply load to some adjacent system if that system needs to buy power through the network interconnection.
Before we go to a story of the Shippingport station, could you tell us some of the unique features that we should look for in this story?
The general layout of the station itself is, of course, one of the unique features. It is contained in 4 large steel containers located in concrete block structure partially beneath the ground. In the center is a sphere 38 feet in diameter with a domed top. Inside of this sphere is located the reactor vessel. The reactor vessel contains a nuclear core where the atomic fissioning takes place and where the heat is produced. On each side is a 50-foot diameter steel cylinder. Each of these cylinders contains 2 of the primary coolant loops. The cylinder at the left is cut away to show the pipe coming from the reactor vessel, to show the steam generator, pumps, valves, and other pieces of auxiliary equipment. The nuclear core, which is contained in the reactor vessel in the central cylinder, is of the seed and blanket type. By that I mean we have a combination of highly enriched uranium in the form of a square annulus, and inside this annulus and surrounding it is natural uranium. This was done so that we could minimize the amount of highly enriched uranium required and obtain the maximum amount of power from the natural uranium, which is the cheaper type of uranium. Because we wanted to get a lot of information for the developmental scientists out of this, we put many instruments in the core so that we could determine while the plant was actually operating what was going on inside of the nuclear core. For example, we have instruments to determine the temperature of the fuel elements while they're operating, to determine the pressure and the flow of the water through the nuclear core. The reactor vessel, which houses the nuclear core, is a very large piece of apparatus. It's over 30 feet high, weighs 167 tons. It has walls 8 inches thick of carbon steel. This is probably the largest vessel of this type ever built in the United States. Now, the water that flows through the reactor core and becomes heated is moved by means of special type pumps through the loops and through the steam generators. These pumps are very special in that in order to prevent any radioactivity from leaking into the containers surrounding the pipes, we canned the electrical windings, both the stator windings and the rotor windings, with thin sheets of metal. This means that the hot water is flowing through the air gap between the rotor and the stator, and it means that the bearings for the pump are operating in the water with no lubricant at all, no grease being used. Now, the water that goes from these pumps goes through the heat exchanger section of the steam generators. That is the part at the bottom. There are several thousand small stainless steel tubes in this bottom section through which the primary coolant that has been heated flows. This, of course, is quite a problem because we have many thousands of small tubes which must be welded to massive sections of stainless steel with no leakage permitted, causing a welding problem and a leak tightness problem.
With an idea of what we're to look for, let us see the story of the Shippingport reactor.
On May 26, 1958, on the Ohio River at Shippingport, Pennsylvania, the world's first full-scale atomic power station for the generation of electricity was dedicated. The plant was developed and designed by Westinghouse under the direction of and in technical cooperation with the Naval Reactors Branch of the United States Atomic Energy Commission. The objective was to obtain a nuclear power plant that would be compatible with an already operating utility, as well as a facility for providing experimentation and development for future nuclear power stations. On this basis, the plant was to be built, made possible by the close cooperation of government and industry. These ideas evolved into this schematic plan for the Shippingport station. It would make use of 4 similar loops, all supplying steam to the one turbine. Any loop could be shut down for maintenance or for instrumentation to permit studies and experiments while the plant remained in operation. Behind the successful completion of Shippingport was the blazing of many trails into new territories, the solution of countless problems in physics, chemistry, engineering, manufacturing, and construction. These problems, many completely without precedent, fell into 4 general areas. The first and foremost being the reactor, posing many new and complex problems in the relation of design and technology. Choosing the fuel materials, designing the size and shape of fuel elements, processing fuel materials, manufacturing elements, determining control rod materials and design, creating complex instrumentation for core and plant operations, and designing the reactor vessel. In the second area, there were problems involving the water. What would be the operating temperature in the primary system? How to control the 2,000-pound pressure? How to minimize corrosion? What measure for water purity? In the third area were the problems of assuring complete safety for persons in and around the plant. This involves shielding and the containment of fission products. A first barrier would confine the fuel. A second barrier would confine the primary water. And a third barrier would surround the entire nuclear portion of the plant. In the fourth area were the problems of special equipment. 0 leakage pumps of unprecedented size were required. Large remotely controlled and hermetically sealed valves were needed. Instruments to monitor reactivity from source to above full power level had to be designed. At the Bettis Atomic Power Division of the Westinghouse Electric Corporation, the first problem was tackled, establishing a core pattern requiring reactor physics analysis and thermal and hydraulic calculations. Mechanical design studies and investigation of fuel materials were made. One consideration was that two types of fuels might be used rather than the single type originally proposed. This new concept was that of using seed and blanket. This seed and blanket core would have to survive certain rigorous tests of corrosion resistance to high temperature water, as well as radiation stability, so that the cladding would not tend to rupture. Actually, no such fuels were known, and metallurgical programs for research had to be established. Extensive study verified the use of UO2. With the selection of the proper fuel, the development of manufacturing processes was begun. More than 2 million uranium oxide pellets and 95,000 blanket tubes were made. Fuel rods and bundles were assembled, welded, annealed, and machined. In the meantime, seed elements were being made and sub-assemblies joined. While manufacturing continued, extensive reactor physics was performed to determine the design reactivity of the core. Excessive reactivity, controlled by control rods, had to be provided to compensate for core fuel depletion. To provide for experimentation checks on the calculations, a nuclear model of the core was constructed at the Bettis plant. Measurements made within the plant indicated that the reactivity calculations were substantially correct. The model also provided actual determination of the control rod positions to within a fraction of an inch out of a total motion of 6 feet. The critical assembly also permitted measurements of neutron flux distribution. However, the ultimate checks could only be made at the Shippingport plant under actual operating conditions. At the plant, an elaborate system of Coolidge flow instrumentation had to be provided. Measurement indicated good agreement with physical calculations. Nearly 2 years of design, development, and engineering were required before plans became definite and actual construction drawings were made. In March of 1955, construction began with the clearing of the site. By mid-1956, construction workers numbered in the hundreds. A large part of the concrete shielding had been poured. The container chambers were in place. And the canal section could be identified easily. With the reactor sphere in position, major equipment began to arrive. The 150-ton pressure vessel began its journey to Shippingport and was installed on October 10, 1956. A high order of cleanliness was necessary while the primary system was open during the installation of the thermal shield. The climax of these operations came on October 6, 1957, with the precise placement of the fuel core in the reactor. The steam generator placed outside the plant is capable of producing 100,000 kilowatts in anticipation of future core development. The Shippingport plant was completed and full power operation was begun approximately 3 years after the start of construction. Total elapsed time from the award of the contract was 4.5 years. Control of its operation is divided into 3 parts: reactor, steam generation, and power generation. In addition, extensive instrumentation provides a vast supply of information never before available. On December 2nd, 1957, the reactor went critical for the first time. This was the 15th anniversary of self-sustaining nuclear fission since the world's first reactor at Stagg Field in Chicago. On December 18, 1957, with the generator synchronized with the Duquesne Light Company system, the first step was made to go to full power. The full output of 60,000 kilowatts was reached 5 days later, and the city of Pittsburgh was lighted through the aid of atomic power at Shippingport.
We've just seen some pictures of the canal used in handling some of the radioactive materials. John, I wonder if you could tell us a little more of some of the problems associated with the handling of these materials.
The irradiated fuel from this reactor can be removed as a single unit by taking off the pressure vessel head and removing it all at one time. Or they can be removed element at a time by opening a special port in the reactor vessel head and taking out one element. In either case, we flood the canal and have water over top of the reactor vessel opening for a number of feet to completely protect the personnel doing the operation using the water as a shield. Then, entirely submerged in this canal water, the fuel can be moved to the adjoining area, and there it can have preliminary evaluation made and be prepared for shipment to the Atomic Energy Commission's reprocessing plant. This shipment is made with the fuel in heavily shielded containers so that there is absolutely no danger to any people.
What are some of the measures that are taken to assure that we can operate a nuclear plant with complete safety?
Well, so far as letting the fission products get out, we use what we call the 3-barrier concept. The first barrier is the cladding of the fuel. The fissioning takes place within the fuel, and the fission products, the halves of the split atoms, are completely contained in a zirconium cladding. Then these fuel elements are located inside of the reactor vessel, with all of the pipes connected to the vessel and all of the places where the water flows being completely hermetically sealed from the rest of the plant. Then the third barrier is the large steel containers that surround the plant and prevent any possibility even of the leakage water from getting to the outside.
Will you compare the nuclear plant with the more conventional coal-burning plant as regards the advantages and potentials to a public utility?
Today, the coal-fired plants are, of course, cheaper. The cost of coal undoubtedly will rise as the coal reserves are depleted and as the cost of mining goes up. we expect the cost of power from nuclear energy to come down as developments take place and we're able to learn better how to build these plants. Someday we expect the nuclear energy to be a cheaper form of energy than the fossil fuels.
With these as the advantages, what is the principal disadvantage of the nuclear station?
Well, it's somewhat more complex, both in design and in operation. And of course, as I said, the main disadvantage today is the cost.
Since the pressurized water reactor, Mr. Simpson, is one of the older reactor types, and we have had newer reactor types developed since it was first conceived, could you tell us how the PWR compares today with some of these newer reactor types?
In 1953, when the Commission decided to build the Shippingport plant, the pressurized water type was the only type that there was sufficient technology existing to be able to build with a good chance of success. Since that time, many developments have been completed in many laboratories throughout the country. A number of small plants have been built. But as we look at the Shippingport plant today, we do not feel that it is an obsolete plant, but we feel that it has some real advantages as a nuclear plant for an electric utility system.
Thank you very much, Mr. Simpson, for talking with us. Mr. Simpson has told us how carefully we must construct the major components of the pressurized water reactor. He's also told us about some of the safeguards which are employed to assure complete safety when we operate these nuclear reactors in populated areas. We have learned that the pressurized water reactor is playing an important role today, producing primarily knowledge so that we will know how to operate this kind of reactor, that we will know the cost picture of it. Thank you very much for visiting with us on this discussion of the pressurized water reactor in the power station and the public.
Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center. In cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, the power station and the public. Your host, Dr. Warren Witzig, Manager of Reactor Physics. Special guest, Mr. John W. Simpson, Vice President and General Manager, Bettis Atomic Power Division. Technical Advisor for the series, Mr. Edward R. Sanford. Engineering supervision by Frank Stuckman and Stephen Zorbas. Production and direction for the series by John W. Ziegler and Robert E. Potts. This is National Educational Television.